The moons of the planet Mars are nothing like Earth's moon. In fact, Mars moons are nothing like what most people would imagine constitutes a moon at all. They are incredibly tiny, irregularly shaped rocks that, if anything, look more like asteroids than moons. Nevertheless, Phobos and Deimos have very neat and tidy orbits around Mars, which isn't at all what you would expect were they captured asteroids. Well, today, we have established theories for the formations of all other planetary moons. The precise way Mars got itself two tiny moons remains somewhat unresolved to this day. It was August of the year 1877 when Asaph Hall, an American astronomer based in Washington DC, discovered the moons of Mars. While speculations about Martian moons can be traced all the way back to Renaissance astronomers like Johannes Kepler, Hall had only recently become interested in the subject due to Mars making a rare close opposition to Earth that year. According to Hall's own calculations, any Martian moons should be very close to Mars, making them hard to spot from afar, as Mars's glare would have naturally obscured them. Despite poor weather conditions that week, Hall's observations paid off, with Deimos discovered first on the night of 11 to 12 August, and Phobos' discovery following just 6 days later. Just as Hall had predicted, these were tiny moons that orbited very close to Mars. And the prevailing theory, immediately following his announcement, was that since these moons felt like asteroids, looked like asteroids and smelled like asteroids, they simply must have been asteroids that Mars had managed to capture into planetary orbits. But, as the 20th century followed and we steadily learned more and more about Phobos and Deimos, that theory would become increasingly shaky. As mentioned, the first moon Hall discovered was Deimos. Deimos is the outermost of the two Martian moons, orbiting the red planet at an average distance of 23,500 kilometers, or roughly 7 planetary radii once every 30 hours and 18 minutes. In this orbit, it has both an extremely low eccentricity, with its distance to Mars varying by just 15 kilometers per orbit, and a low inclination to the planet's equator by just some 1.8 degrees. The object itself is named Deimos, after the Greek god of dread and terror, one of Mars' sons. Deimos is a small, irregularly shaped object with an average diameter of just some 12.5 kilometers and a mass of 1.5 exagrams, giving the moon a very low density of just 1.5 grams per cubic centimeter, which is only slightly more dense than PVC plastics. Such a low density indicates Deimos has plenty of underground voids and loose regolith on the surface. And indeed, the surface of Deimos appears very smooth, with most of its craters buried beneath dozens of meters of dust, which makes sense if the regolith isn't very rigid. Deimos' dusty surface appears vaguely reminiscent of Mars's, and has a very low reflectivity, and thus Deimos appears very dark with an albedo as low as 0.07, making the moon very faint. The second moon Hall discovered was Phobos. Phobos is the larger of the two moons and orbits much closer to Mars. With an orbital radius of just 9,400 kilometers or roughly 2.75 planetary radii, it flies just 6,000 kilometers above the Martian surface. Phobos' orbit is actually so close to Mars, it's slowly decaying, approaching the red planet by some 2 centimeters every year. In its current orbit, it goes around Mars once every 7 hours and 39 minutes. Phobos is named after the Greek god of fear and panic, brother of Deimos and another son of Mars. Another small, irregularly shaped object, Phobos is very similar to Deimos on the overall, albeit a bit more chunky. For starters, Phobos is almost twice as large as Deimos is, having an average diameter of 22 kilometers. Its mass too is about 7 times greater than Deimos is, being roughly 10.5 exagrams, giving Phobos a more compressed, low density of 1.86 grams per cubic centimeter, which suggests a more compact and less porous interior, Consequently, the regolith layer on Phobos is suspected to be a lot thinner than on Deimos, with its surface not being nearly as smooth. It's even darker than Deimos though, with an albedo as low as 0.06, making it one of the faintest moons in the entire solar system. As mentioned, when Phobos and Deimos were first discovered, the immediate assumption was that these moons were actually captured asteroids originating from the main belt. After all, Phobos and Deimos, at least superficially, bear some striking similarities to some types of asteroids. They're small, irregularly shaped and with low albedos, which matches types of carbonaceous chondrite asteroids. The idea that Mars, which orbit sits on the inner edge of the main asteroid belt, could have at some point in its 4.5 billion year long history plucked 2 asteroids from the belt sounded entirely plausible. In the late 19th century, we still didn't have good theories for the origins of our own moon, let alone those of other planets. So this assumption that Phobos and Deimos were once asteroids, plucked from the main asteroid belt by Mars's gravity, stood unquestioned for decades. Yet, what would seem like the most logical scenario for the origins of the moons of Mars is today but a minority viewpoint among astronomers. Indeed, as of this video, the origin of the moons of Mars still hasn't been definitively solved. As the 20th century progressed, and as astronomers gradually started to gain a better understanding of the orbits of Phobos and Deimos, cracks in this theory first began to appear. For starters, the orbits of Phobos and Deimos just seem way too neat and tidy for captured objects. A captured object could have come in from any direction, so it would be pretty unlikely for it to end up orbiting prograde along the planet's equator. If it were just one moon, that might just simply be a coincidence. But since both moons orbit in the same direction on roughly the same plane with low eccentricity, only a rather elaborate capture scenario, such as having them be captured as a binary asteroid, would have to be constructed in order to explain their current orbits. And when in the 1970s the Viking missions provided us with the first up-close insights of Phobos and Deimos, even more cracks began to appear in the theory. So did Phobos' grooved terrain become apparent, something not at all common on asteroids. And spectral analysis of the moons also revealed the presence of hydrated minerals, which seems more consistent with Mars itself than with typical asteroids. Furthermore, the morphological differences between Phobos and Deimos also made them having previously existed as a binary a lot less likely. All by all, while a capture scenario is definitely not impossible, Occam's razor suggests something else might have given Mars its 2 small moons. So, let's look at some other theories to explain their presence. If it's true that Phobos and Deimos are composed of similar material as Mars, then they most likely formed in situ around Mars, either from the same material that originally formed Mars, or later from Martian material ejected into orbit. This leaves the door open to construct multiple interesting accretion scenarios. But first, what is accretion? In the early solar system, our newborn sun was surrounded by a vast disk of dust and debris left over from its formation. Inside this disk, over time, small particles gravitated together to form clumps of mass. As these clumps gathered more mass, they gained more gravitational pull, and the accretion process escalated to eventually form the planets. Some of the planets grew massive enough to capture disk material into orbit, forming their own miniature accretion disks around them, from which in turn their moons accreted. Could it be so that Mars formed with its own miniature accretion belt, allowing for Phobos and Deimos to form from the same material as Mars did? In short, no, not really. While such planetary accretion disks work neatly to explain the origins of the outer giant planet's moons, Mars was almost certainly never massive enough to have ever hosted its own accretion disk after formation. It often goes unmentioned that Mars is only half the size of the Earth, and being only 11% as massive. And even the Earth most likely never had its own accretion belt, so this scenario cannot explain the origins of Phobos and Deimos. So if Phobos and Deimos didn't form from the same material that originally formed Mars, then perhaps they instead formed later from Martian material ejected into orbit. In the case of Earth's moon, we now understand it was formed through a giant impact event. Early on in our world's history, the Earth was hit by a Mars-sized protoplanet called Theia at a low 45-degree angle. At such a low angle, the impact ejected a large amount of mass into orbit, which then went on to form our moon. This wasn't true accretion though, as simulations show that the moon was able to form very quickly after this impact, possibly in just a few hours. If true, that means the Earth never had an accretion disk around it either. Since this scenario neatly explains the formation of Earth's moon, could a giant impact event also explain Phobos and Deimos' origins? There is some tentative evidence that Mars experienced a giant impact in its past. The northern hemisphere of Mars has an elevation that is on average at least 4 kilometers lower than its southern hemisphere. The crust here is much thinner and younger than in the south. Could that be because the entire northern hemisphere of Mars is actually a giant impact basin? This theory seems tempting, but for starters, rapid formation wouldn't work for Phobos and Deimos. Their small sizes and low densities pretty much demand an accretion scenario where they took their time to form. Unfortunately, models have consistently failed to show how a giant impact event could create an accretion disk around Mars. The Borealis Basin, being an impact basin, is also not a settled debate, with a number of alternative explanations still possible to explain its formation. So, while an impact scenario is possible, there are yet better theories to explain the origins of Phobos and Deimos. Another scenario for the origins of Phobos and Deimos seeks to create a Martian accretion disk without an impact. Earlier on this channel, we had a look at the impacts of Comet Shoemaker-Levy 9, which was one of my favorite videos I ever made, so I'll leave an info card in the top right of the screen if you want to go check that one out. But in that video, we saw how prior to impact, Comet Shoemaker-Levy 9 was disintegrated by Jupiter's gravity after encroaching its Roche limit. The Roche limit is the minimum distance an object can orbit around another celestial object before which tidal forces overcome its own gravitational force. So, when Comet Shoemaker-Levy 9 approached Jupiter too closely, it was torn to shreds by its tidal forces and fragmented into dozens of smaller pieces, which then went on to impact Jupiter one by one. But fragmentation does not always necessarily have to conclude with an impact. A 2024 simulation by NASA shows how an object might have been disintegrated after a close Mars approach, but with the debris remaining in orbit instead of impacting. Eventually, the debris was pulled into a ring around Mars, from which Phobos and Deimos later accreted. That might sound far-fetched initially, and trust me, it's definitely not straightforward, but the approacher wouldn't have actually needed to be all that massive to allow an accretion disk to form. The main issue weighing this theory down, however, is that it fails to explain the apparent similarities in composition between Mars and its moons. So perhaps still something else might have happened to form the Martian moons. The final, and perhaps currently the best suited theory to explain the origins of Phobos and Deimos, posits that Phobos and Deimos did accrete around Mars, but not from any impactor or passerby, but rather from the remains of a former Martian moon. In this scenario, Mars, in the past, possessed a single larger moon that ended up spiraling inwards until it was ripped to pieces by Martian gravity after crossing the Roche limit. Some of its debris then remained in orbit, forming a delicate ring structure around Mars, from which in time, Phobos and Deimos then accreted. This theory came about when some tentative evidence was discovered by Mars rovers that in the distant past, when Mars still had surface water, it might have had tides. Since Phobos and Deimos today are way too small to cause tides, that might suggest that Mars had a larger satellite orbiting it at that time. While that falls far short of evidence, it makes a tempting theory. especially if that old moon formed alongside Mars, it could explain why Phobos and Deimos today appear similar in composition to their parent planet. Today, Phobos' orbit is slowly spiraling inwards at a rate of about 2 cm per year. At that speed, it is expected to cross Mars' Roche limit within the next 40 million years and be destroyed. Deimos, on the other hand, is slowly escaping Mars at about the same rate, and it will eventually fly off into space on its own. If we extrapolate that backwards, the orbits of Phobos and Deimos overlapped sometime between 1 billion and 2.7 billion years ago, giving us the strongest evidence yet that they share a common origin. Ultimately, more studies will be needed to definitively make or break any of these theories and resolve the issue of how Mars got Phobos and Deimos. A big step towards this goal will be studying the material from which Phobos and Deimos are actually made. Previous attempts to get close to or land on Phobos or Deimos have all resulted in failures. The Phobos 2 probe by the USSR got very close, but most heartbreakingly lost contact just before it could deploy its lander. Another attempt by the Russian Federation failed to escape Earth orbit entirely and ended in failure too. But this year, if you're watching in 2026 at least, the Japanese space agency JAXA is expected to launch the Martian Moons Exploration, or MMX for short, program, part of which is to deploy a lander to Phobos and conduct a sample return mission to Earth. For this purpose, the mission will include a rover to deploy on Phobos. Developed in collaboration with France and Germany, the Idefix rover, cutely named after Idefix from the Asterix comics, will be the first rover to land on Phobos. Due to Phobos' extremely low gravity, the lander will have to be deployed from just 100 meters above the Phobian surface, and freefall for about 90 seconds before landing at a speed of about 1 meter per second. On Phobos, the gravity is so low you can achieve escape velocity with a BMX bike and a ramp. So, because of that, to move about safely on Phobos, the Idefix rover will need to limit its speed to a measly 4 meters per hour to conduct its mission. Idefix will scout out the optimal sample collection site, after which another module will be deployed to collect some 10 grams of regolith and launch off again. If all goes well, this mission will deliver the sample back to Earth by the early 2030s. Perhaps then, finally providing the true answers as to how Mars got its 2 tiny moons. Without a doubt, Phobos and Deimos will continue to intrigue us for a long time to come. In this video, I focused on just one aspect of them, their origin story, because I think it's really interesting how what seems like the most sensible and logical theory of them being captured asteroids just doesn't match our scientific findings. And I think it's a wonderful case of astronomy being awesome, and I at least will definitely be following the findings of Idefix and JAXA when it lands on Phobos next year. So I really hope you enjoyed this video. If you made it all the way to the end, leave a comment and a like, it really helps me out massively as a small channel, and maybe consider subscribing. I do all kinds of science videos and world building on this channel, so if that's something up your alley, stick around and subscribe for more. As always, thank you so much for watching, and I'll see you guys in the next video.